Hello and welcome to the next video for csc314 assembly language. This should be week 5 video number 3 here. What we're going to be looking at is more indirect operands, in particular those requiring expressions or calculations to arrive at the desired address. In particular, we're looking at a few examples where the address is calculated. Here we're using the address just in a plain register, so there's no calculation inside these square brackets, but the whole process is going to be doing a calculation, arriving at values in these registers to decide what address we're moving data to or from. But down here we're seeing another situation where we use two different registers to determine the address. We start with a register and then we add 4 times value in another register. This is a typical way of having an array, of working with an array where basically one register is acting as an offset. The multiplier is the size of the items in the array. In this case, this is just standard double words or 32-bit integers. So we need 4 bytes per integer, and then we have an address of the first element of the array. So take that first element address plus 4 times the index gets the address of an element that we want. That's the basic idea in a nutshell, what we're looking at in this video. So we're basically dealing with how do you actually work with things like arrays in assembly language, and this basically shows you. And how does the indirect operand work as an address or a pointer? And depending on how quickly you get this, you maybe just that quick explanation was enough, but the rest of this video we're going to look at this in detail and make sure that you understand what's going on. And what this program that you see before you is going to do is it's going to take some data in memory. So we're defining a couple areas of memory here in the .data section. And here I have defined an address text that's pointing to the first byte of these 26 bytes of data here. These 26 bytes I'm using a string to define. And that's just A, B, C, D, E, F, Gs. That's just the ASCII codes for these symbols will be stored in those 26 bytes of memory starting at this address text. Then I also define a text len symbol that takes the current byte position minus that last address. So that difference should be 26 as long as I did not leave a letter out of my alphabet here. So that should be 26. Text len will just be 26. Then primes will be the address of the first byte of this series of double words. I'm using DD here. DB stands for data bytes. DD stands for data double words. So the first D is data, the second D is double word. And so each of these numeric constants that I'm putting here is going to be translated into a 32-bit integer and saved in 4 bytes of data for each one of these. And I believe I have 15 of them. And it would be nice to have a constant that I can refer to that tells me how many numbers I have here. And so I again use this $ notation and the EQ directive. And what this says is it's going to define this symbol here to be the current byte position minus this address. So that difference will be the total number of bytes I need to store all of these numbers. And then I'm dividing that by 4 so that I will get the actual number of words, not the number of bytes for this. So that tells me how many items are here. Basically, what these two things do are defining an array. This is basically defining a character array of 26 elements, and it's initializing that array, pre-initializing that array with data. This is effectively declaring a 15 element array of integers and initializing all 15 elements with data. That is effectively what these lines in this program do. So what are we going to do with this data? Well, until I show you in more detail how to get input and output from your assembly language programs, you've already seen the sys rate, so you could get some output if you followed that example. But we'll be covering that pretty darn soon. For now, we're just working in memory, and all I want to do is write in memory, in the computer's memory. I just want to take first, I'm going to take the character array, this string, and I'm going to reverse it. Actually, I should not call this a string. Shame on me. I'm going to put that in all caps here, if I can. Should not call this a string. Now, I wish this was a class, because now I would ask, who knows why this is not a string? Do you know why it's not a string? It looks like a string. It's a bunch of text in double quotes. That's what we call a string in C programming, right? And in most programming languages. There's one very specific reason why this is not a string. And this is not a string because it does not have what's called a null terminator. And something strange is going on. Somehow, I'm not sure how, but okay, it's back to normal. Something weird happened there. It kept wanting to highlight text and wouldn't let me do much else in my virtual machine there. Not exactly sure what happened, but it's not worth trying to figure it out either. So back to what I was saying. Why is this not a string? And the specific reason is because it does not have what's called a terminal. A null terminator terminal. I'm not speaking very well tonight, I guess. Does not have a null terminator. Now, I don't know if you would have been taught this already about strings. But what makes a string when you're looking at data in a computer is the fact that you have a sequence of bytes, a sequence of non-zero bytes, particularly. Usually we're talking about ASCII codes, but when you get into Unicode and so forth, there's other kinds of strings. But you're talking about a series of non-zero bytes until you get to a byte that is a 0. And that byte that is a 0 tells you that you are at the end of the string. And that is the official way to know that the string has ended. Here there is no 0 byte. It's just 26 bytes that may or may not be 0. It's not a string. Okay? If I wanted this to be a string, I would have to add a byte to the end of this, like that. Now this would be 27 bytes, and the last byte would be a 0, making the whole thing a string. And so whether or not something is a string, at least in some contexts, requires you to actually look at the data and make sure that you have a null terminator. If you don't have a 0 byte to indicate the end of the string, then you technically don't have a string. And a lot of programming languages, a lot of functions that are designed to work with strings will suddenly have huge problems if you don't have that null terminator. So that's just a little tidbit aside. We may talk about that distinction about strings more later on, but I thought I'd throw that in there because I was misusing the word, and I don't like it when I catch myself misusing a word. And I figured I might as well clarify that. So that is not a string. Actually, I can leave that part of the comment in there. let's just leave the, it should not call this a string comment in there but I'm going to delete the null terminator stuff just because that's too much. All right, there. We'll leave the comment that way. So I recommend, and generally I recommend, as you're following my videos, type in the comments too. The comments serve you as notes, as reminders. Just the fact that you physically type in these comments, you're more likely to remember whatever it is the comment is trying to teach you or explain or whatever. So type in those comments, keep these files saved. There are things you can refer back to. So anyway, moving on. So we've declared and initialized an array of 26 bytes there and an array of 15 double words here. So 15 double words, each double word is 4 bytes. So that would be 60 bytes. So we're declaring and initializing an array that is 60 bytes long of 15 double words. Okay? And again, just remember that. In fact, when I was preparing this video, I put a DW here. Well, W here just stands for regular word, and at least in NASM assembly language, regular word refers to a 16-bit or a 2-byte chunk of data, not a 4-byte chunk of data. You should be aware that the word does not have any absolute meaning in computer science. Sometimes just 1 byte can be considered a word. Sometimes 2 bytes is considered a word. Sometimes 4 bytes is considered a word. And people will just say word when they mean 4 bytes. But in the NASM syntax, at least here, word specifically means 2 bytes. Double word means 4 bytes. So DD there for double words. And so that's all reserved. Now, down here, I'm finally using the .bs section. And again, generally, this is where you're going to put uninitialized. You're going to reserve chunks of memory that are not initialized. And so I'm defining 2 addresses. The somewhere address points to the first byte out of a 100-byte buffer. Now, about this word buffer, you may or may not have used this word much so far in any programming context, but typically the word buffer refers to a character array which will in some sense serve as temporary storage for character data. That data may or may not be in the form of a string with the 0 terminator that we mentioned earlier, but it is a place to store character data. So that's just a little bit of kind of traditional terminology. When we talk about a block of memory, in this case 100 bytes, B for byte there, 100 of them, we're talking about, we tend to call that such a block of memory a buffer, particularly if it's going to store text information, ASCII bytes. It could store binary data. A buffer can be applied to any kind of data, but this is fairly common. Now we also have this address elsewhere that's going to point to the first byte that we are reserving here, and here we are using the res D keyword, and that's again D for double word. So this means reserve 100 double words. Okay, so how many bytes is that? That's going to be 400 bytes, right? And think of it this way, it's maybe better to think of this as an array of integers. In fact, I'm saying an array of 4-byte double words because we could use those 4 bytes, each chunk of 4 bytes, we could use those 4 bytes for anything. We could even use them for little chunks of 4-byte chunks of text. That's fine. But in our case, we're going to think of this as an array of integers. Okay? And specifically an array of int, just like C. Okay, but this is our interpretation. It's up to us to write the program in such a way that our interpretation actually makes sense. So, similarly, we can say our interpretation of this is an array of car, i.e., This would be just like car. This is almost like car somewhere 100 in C programming. So compare to that. So compare this to int elsewhere 100. Yeah, and that makes my comment a little bit too busy, so I'll take the just like C out. Let's do it that way. There we go. Yeah, so hopefully that kind of makes sense what we're doing with these lines down here in defining our data and defining basically some array variables. But keep in mind that in assembly language, what you normally would think of as variable names are really just addresses. So text, primes, somewhere, and elsewhere are all going to translate into specific addresses, and the addresses they translate into refer to the first byte of each of these blocks of memory. Okay? Now again, this 100 here is not data, it's telling us how many bytes. This 100 here is telling us how many double words. So the resb and resd keywords work quite a bit differently from the db and dd keywords. Here, the db keyword, you don't tell it how many bytes you're going to define here. You just start listing the bytes of data that you want, and it takes as many as you give it. All right? So if you actually want to have a number referring to how many there are, you got to do something like this, especially if you think you might go editing and maybe you delete some characters out of there. Then the next time you build the program, at least this text-len symbol will have the right value. Down here, you might want to define a symbol that is 100 and then use that. So maybe you want to define a size symbol and say that's EQ 100, and then we can come in here and do size. Might as well do that. And there's no reason those two things have to be, there's no reason the character array and the integer array have to be the same number, the same size. I just happen to make them that way, just to make them big enough to hold whatever it is I'm going to do here. Because what am I going to do? I'm going to have a program that reverses them. So we're basically going to take the data in the text array, so to speak, and we're going to copy it backwards into the somewhere array. And then we're going to take the numbers in the primes array here, and we're going to copy them in reverse order to this elsewhere array. And those actions give us a pretty good example of using calculated addresses in a systematic way. It also gives us pretty good examples of working with arrays in assembly language. And so what's left to do is to build, run, and observe this program in Katybug. So let's go ahead and get that out of full screen. So now if you need to see everything, you're going to have to pause and back up to where I have the whole thing displayed so you can catch up. So go ahead and pause as long as you need to. Get this all typed in, and then let's build and run it. Okay, so to build it, the usual NASM command. Of course, again, you need to remember your debugging options here in the NASM build command, and then we do the LD command to do the linking, and finally we are going to run Katybug on our new program called Reversals. That's what I named it. So the source code file, reversals.asm, executable file, reversals, and let's run that in Katybug and see what we've got. And I've already been playing with this to prep for this video. So I had some breakpoints in there already. I'm going to take it out and start over. So let's see, I'm going to actually maximize this so we have as much room to see stuff as possible. Also, I'm going to show you something. You can move these tabs around, and I think they're actually more useful if they are all over here. How you drag and drop them is a little bit strange, though. So, like, I'm going to take this memory window, and I'm going to combine it over here with the locals. Whoops. And, of course, it didn't combine. There we go. Now I have locals and memory. Locals is not much use to us right now. It would be much more useful if you're using this to as a debugger on a C program. There will be ways we can look at that. But for now, we're not terribly interested in locals. We're interested in memory. And likewise, we use the registers. And you don't grab it by the tabs down here. You grab it by the title here. And I can bring that over, and let's see if that got it. So drag that. Now I have registers in memory over here. Breakpoints is another one we might want. Drag and drop that. Okay, now we've got all those in there. Might as well drag them all up in here. I think just combining them all into one, usually more worthwhile. Might as well bring them all in. Why not? The other option is just to get rid of a few of them. The only ones that we are really that interested in are, of course, memory and registers. So we'll play around with those. Actually, registers, maybe if I had one of them separate, that might be kind of cool. So let's go ahead and bring registers out down here. Actually, I brought memory out. There we go. So now we can have registers here, memory here. We can see memory and registers at the same time, and they're fairly tall. I wonder if it'll let me do more side by side. Ah, yes. Notice how I'm doing this? So I'm dragging it over there. That's going to tile it side by side. Now I can have my memory and registers side by side, really tall. And see more stuff all at the same time. I think this is a more useful layout here. So you can decide what layout you prefer, but I thought I'd show you that because I think this will be more convenient for viewing what's going on. So let's go ahead and set a breakpoint, and then we're going to just look line by line what's going on here and how this works. It might actually be easier for me to explain looking in the editor, just because it's a better way to look at the program. So let's look at what we're doing here. I'm taking the address text, so the address of this letter A here, and I'm putting that into register ESI. So ESI is now going to serve basically as my pointer. It'll basically be my pointer to the beginning of that character array, okay? And specifically the character array text. And then ESI, I'm going to add the length of that array to that pointer. So what does that mean? That means I'm adding 26 to text, and that's still going to be in ESI. So now ESI is pointing to 1 byte after the end of the array. It's pointing to the next byte after the array. That's because, again, if text length was 0, then that would be pointing to the first byte. It's just keep in mind zero indexing, zero-based indexing, and that should make sense to you. So finally, I'm subtracting 1 from ESI, And so now ESI is pointing to the last byte. So now ESI is the address of the last byte, as we've commented here. And what else am I doing? Now I'm going to take this variable, or this address somewhere. This is where I'm going to copy the array in reverse, and I'm storing that into EDI. So EDI becomes a pointer of my destination. Let's call it a destination character array, which I called somewhere. Then I basically just have a loop, and what's going on in this loop is I'm just going to increase the destination pointer by 1, decrease the source pointer by 1, and swap, and then copy 1 byte at a time, copy from one place to the other. So we'll see specifically how that happens. So I take ESI and I use square brackets because that says go get what's in memory at that location. If I took off the square brackets, that would be saying, that would be attempting to copy the contents of ESI to AL. All right, you can't do that for, well, you can't do that period, because ESI is a 4-byte register and AL is a 1-byte register. But it's also not what we want to do. We want to go grab that byte out in memory that ESI is pointing to, okay, and move that into register AL. Then the next step is take that byte in register AL and move it to where EDI is pointing to, because that's pointing to where we want to put it. Then we decrease ESI by 1, so that ESI, so initially, remember, after we did these 3 steps, ESI is pointing to the last byte in our character array, in our source character array. So basically, ESI would be pointing to this byte here, the character Z there. And EDI would be pointing to the first byte that we've reserved here. All right? And so we copy the Z into AL, then we take the Z from AL and copy it to that location there. Then we decrease ESI, increase EDI, and that way we're pointing to the Y, and then it's going to loop back and do the same thing. That's the essence of it. So you can look at the full details of these commands. Well, let's actually look at this now in KDebug and see it in action. So let's hit run. Now that it is actually running and paused, now we can see the register variables. Most of these we're not that interested in over here. Over here in the memory, let's look at actually, we don't want to look at somewhere. First, let's look at text. So I'm going to put ampersand text there. And with that view, we probably want to look at bytes and character. So here we're seeing it as, well, we've got plenty of room, so let's slide things over a bit. There we go. So now we're seeing A, B, C, D, E, F, G, and so forth. So starting at address 80490CC, that's the address of somewhere. We have these characters right here. So that's our 26-byte array. Notice that after the Z, there is not a null terminator, and even if there was, it would just be accidental. Because the data after here is basically, we can consider this garbage data. Certainly, we as programmers did not determine what this data was going to be. Okay, so we can see what's in that location in memory. So now let's look at somewhere. Somewhere is just a bunch of zeros, okay? If we look at it as bytes, it's showing the numeric value of 0, then it's showing the octal character value. So you have single quote \000. That's actually C programming notation where you can use octal to represent the ASCII codes of characters in a string. So \0000 is the character whose ASCII code is 0, which would be the null terminator if we were working with strings. All right, so that's what's in that array. Now let's actually start doing some steps. So we took the address text and we stored that in ESI. So here in ESI, we should see that. I think it'll look better if we use hexadecimal. Whoops. I'm going to change that display to hexadecimal. So now in ESI, we have that 080490 CC address. Okay, remember that is the address of text. That's what text is. The address of this lowercase a right here, this byte stored there, that byte. So we've moved that there. Now we're going to add the value of textlen to that. What I want to do is, let's go ahead and put underscore start here, and then do an instructions view on this. Boom. All right, so at start, the second instruction, which is where we are right now, let's add a hexadecimal 1A to ESI. Now, what is 1A? That's, think about it, figure it out, think about it. Should be obvious. Pause, figure it out for yourself, then come back. You came back, and it was obvious, right? 1A, that's got to be 26. That's supposed to be the length of our alphabet. Alphabet has 26 letters in it, right? So, remember, textlen was equal to $ minus text. So that's current byte address minus whatever number I give here. That's the address text. So the current byte address minus the address from 26 bytes earlier is 26. Textlen is 26, giving us the length of the alphabet. So textlen should be 26. So if we look at 1A, well, that's 1 times 16 plus A is 10 in hexadecimal. 1 times 16 plus 10 is 26. So it all makes sense, right? Okay, so now we're going to add that 26 to ESI and get a new address. So let's step over. And now ESI has this value in it. Same initial digits, E6 are the last 2 digits there. And yeah, okay. So the next thing that's going to happen is we're going to subtract 1 from that. But before we do, let's also look at primes, right? Let's see what the address of primes is. I think I already had this in here from when I was testing earlier. So there's primes, and the address there is 80490E6. 80490E6, which is the current value of address. Now, why is that? Well, if we start with the address text and we add 26, text is the address of A, plus 26 would be the byte immediately after this byte that has the Z in it. Well, the next byte is the first byte here. So defining these constants, these symbols here, just giving them numeric values, these are not representing any data that's going to be stored in memory when the program loads. So they don't have any effect on that. So the next actual bytes of data that are represented in our program here are given here. So primes, that's the address of the first byte of these, and the first byte of these is the first byte after this character Z right here. So that is why after we took the address text and added 26 to it, we ended up with the same address that primes represents. So now let's come back to our program. We're about to subtract 1 from ESI. So let's go ahead and do that. And boom, we've done it. And now this address is pointing to that letter Z. Let me get, what do I want? I want text. So the address of this Z right here, notice that the Y has address 80490E4. 804. So the Z will have one higher than that. So the Z will have 80490E5 will be the address of the Z. So here we have it. We have now the address of that letter Z stored in ESI. So far, so good. Now our goal is to reverse the text. So when we're going to be copying the text into this buffer called somewhere, and we want it copied in reverse. So the next thing we do is we take the address of somewhere, we put that into EDI, and so EDI is going to be our pointer to where we want to copy the next character. And so we take somewhere, put it in EDI, and so EDI will have that address in it. So step over, and now EDI right here has the destination address. So basically the next thing we want to have happen is to copy the Z from here into that byte there. Right now there's just a bunch of zeros there, looks like. If we come over here, just a bunch of zeros. Brrr. So, but this is the first byte of somewhere, so what we're expecting is for that Z to be copied here. Okay, that's what we want to have happen next. Let's see if it actually happens. Well, we have to step this instruction. That instruction did a move the byte that's pointed to by ESI into register AL. Register AL is the last byte in register EAX, so there's that 7A. Did we move the right thing? Let's go back and look what we moved. Let's see, we need to go to text. So there is the A, so we copied, no, I'm sorry, we're copying the Z. So the Z, which is 122 in decimal, okay, is copied here. So what is 7A in hexadecimal? You guessed it, 7A in hexadecimal is 122 in decimal. 7 times 16, that's, let's see, 70, 112 plus 10 is 122. Or we can switch and see that as a decimal value, or we can see it as, let's see, well, does it give us a character option? It's not giving us a character option here, I guess. So we don't get to see this as a character, but we did get to see its ASCII code as a decimal number of 122. So we see that we copied the Z into register EAX. Specifically, we copied it to the first byte of EAX. All right. Now, our next step is going to be to copy that same byte out to memory to our destination, which is being pointed to or addressed by EDI. So we're going to do the step there. So let's do a step over and see that that happened. If we come over here and look at somewhere, and now we see the letter Z, the character Z, the 122 ASCII code, that byte has been copied somewhere, specifically here. Okay, now if we just keep stepping over, we see that we've got a loop that's repeating. Now I haven't given you the details on this loop. So after we do the two copies, we decrease ESI by 1. That's the dec operator. That's just decrement, so it's just subtract 1 from whatever register you give it here. This is the increment operator. Increase this register by 1. So we're decreasing a register by 1, increasing a register by 1. And then to know whether or not we should continue with the loop, I do a comparison. I compare ESI with text. So remember, ESI is, we started ESI larger than the address text because we added the number of bytes to it, subtracted 1 to point it to Z. So ESI should be pointing, we've done a few, so I think it's pointing at the W or the V right now. So it's at here, so that's a higher address than the address text. And we want to keep going as long as it's higher than text, but it keeps going down by 1. And when it's less than text, then we know we're ready to stop. So how do we do that? Well, we compare ESI, the address stored in register ESI, to the address text. And if I click this little plus sign, we can actually see what that's encoded as. So you can actually see there's the address, there's the actual numerical constant that text represents. Okay, so we're comparing the number in ESI. Where is ESI? ESI is this number right here. Is that greater than or less than this number right here? And what you can do is you can look, okay, all the digits are the same up to E2 here, and then we have CC here. So E2, well, E is greater than C in the second digit there, so we know that this is bigger than this. And so it should be working out just fine. So if we just keep stepping over, I can click this over and over and over again, and we're not seeing the changes. So let's go back and look somewhere, and we're seeing it fill in. And if I keep clicking, and you can see the green arrow on the side popping up. I guess I haven't really discussed the jump command, but you've already seen jump commands. This is the jump greater or equal to. So it's just doing the jump. If the comparison said that this is greater than or equal to this, then that's true. So we actually do the jump. And so we can keep stepping over and keep doing the loop. And it's going to keep jumping back until we've copied them all. Assuming that I didn't make any mistakes in my program, this will just keep going until we get to the letter A in the last spot. Notice it is filling it in reverse alphabetical order, and it just did the A, and we just did the decrement ESI. So let's look at ESI here, and ESI is now 0804990CB, one less than CA there, so we are now officially too small. It's an address before dash text. So text starts at CC, but B is less than C, so CB, that's a smaller address. It's CC minus 1. So right here, ESI is now one low. The address stored in ESI is one lower than the address text. This compare is going to come out less than, and that's going to set appropriate flags here that jump if greater or equal to is going to look at. This time it's not greater or equal to, so it's not going to jump back to this address of that label right there. It's going to move on with the next step. So if I click step over here, boom. So now you have seen an example. Previously you saw an example of how to kind of do an if-else in assembly language. Now you've seen an example of how to do a loop. And here we went through that loop. And now we're basically going to do the same thing with the array of numbers, but there is a trick or a catch there in terms of how I'm calculating the address. You'll notice that these addresses here involve a calculation that involves two different registers. So there's no way the assembler calculates these ahead of time. There's no way the linker calculates these addresses ahead of time. This is all calculated at runtime. And this is one situation where we can actually talk about three different registers in the same instruction. They're used in a very particular way, but it works out just fine. So basically, ESI is acting as what we call a base pointer, pointing to the beginning of an array. ECX is acting as an index. The 4 is a scale factor telling us what the size of each item in the array is. And so if you take that base index plus 4 times, or if we take the base pointer plus 4 times the index, we get a pointer to the thing we want. And the same thing works here with ECX counting down and EBX counting up. We're going to do the same thing and effectively reverse the array of numbers. So if we look at primes now, here are our primes, okay, starting at 80490E6. we have 2, 3, 4, 5. I've already got this set to view as words. And in decimal, of course, we could look at it as bytes, but then it's not as obvious what's going on. Although these numbers are all small enough that even as bytes, we see the correct numbers. Because they only go up to, what, 41, 43, 47. So even as bytes, it looks right to a human eye, okay? But makes more sense to look at them as words, because that's how we're organizing this information. So now, what are these things, these huge numbers out here? Well, that's just garbage data, so don't worry about those things. They're not anything that is really part of our program or the data initialized or otherwise of our program. So ignore that stuff. That's just garbage data, but the 15 words that we did define are all here, and we are copying them over to elsewhere. So let's look at elsewhere, and I think I already have that defined to be looking at words and decimal. And now we'll step through this. So this is basically going to do the same thing, except for the way we're doing the addressing a little bit differently. So I'm copying the primes address to ESI. That'll be our source address again. I'm copying n primes to ECX and decreasing that by 1, so now I have the index of the last number in my array. So ECX should be 15 at this point. Let's go ahead and do the steps just to see that. So step over, I just put the address of primes into ESI. So ESI now has the address of primes. Right there's the address, and right there's the address. Okay, now we're going to copy n primes to ECX. N primes should be 15 because I had 15 of these here. And just you have to remember how that calculation happened on this line to actually give n primes its value. But so n primes is 15. We're going to put a 15 into ECX. We can actually expand that command and see that there's hexadecimal OXF. F in hexadecimal is just 15. So this means put a 15 into ECX. That's what's going to happen. So we do the step over, and sure enough, we get a 15 in ECX. We can look at that as decimal if we want. See the 15, go back to hexadecimal. You should really get used to working in hexadecimal, so I encourage you to do as much as you can with hexadecimal and just kind of start to mentally make these calculations back and forth. You should just know automatically F in hexadecimal is 15, okay? Now, we're going to decrement that 15 by 1. So now it's an E in hexadecimal, or a 14 in decimal, right? And why is that? Because of zero-based indexing. So the index of that last thing, if we have an array of 15 things, the index of the last thing is 14, right? So that's going to be indexing this number right here is what we want it to do. And when we do the calculation later, when we do this calculation ESI plus 4 times ESX, that will be the address of the first byte of that word. Okay? So, so far so good. So now the other thing is we use EDI to be the pointer to the destinations. So I copy elsewhere to there. So let's do the step there. And so we took the value of elsewhere. Elsewhere is an address that will be the first byte of the 400 bytes, the 100 words, or the 100 double words that we reserved here. Right? So that's what we want to start our destination at, because we're going to be copying the primes in reverse order now. So now, the last thing we do is I'm going to use EBX as the index for those primes. In fact, I want to come over to my program and add a little bit to the comments here. I'm going to say EBX will be the index into the destination array of integers elsewhere, okay? Elsewhere being this right here. And ECX, So ECX here will be indexed into the source array of integers primes. So ECX is going to be, ECX and EBX are going to act like indexes, but we don't get the convenient notation of C programming where you just use square brackets in the index after the name of an array variable. You actually have to calculate the address. Okay, so we have to take the index times the size of the items in the array plus the base address of the array to get the address of the thing we want. And so we're doing that in both of these cases. We have the source index counting down and the destination index counting up. Now there are tricks where we could have, we could subtract ECX from something, or things like that we could do, but this is just how I decided to throw this particular example together. So at any rate, let's come back over here and start to see that in operation. So EBX is the destination index, and it's going to start at 0. So let's do that. And so now we have a 0 in EBX. It was 0 already, so notice it didn't turn red because it didn't actually change. But you shouldn't assume anything about what's in those registers. You should always set the registers to what you want them to be. So now EBX is 0, and here we go. We're ready to do the movement. So now we're going to copy what is at this location into register EAX. This location, once again, that's what's in ESI plus 4 times ECX. So ESI is 80490E6. ECX is a 15 or is a 14. So 4 times 14 is whatever it is. And you add that. If you do it all in hexadecimal, then it's going to look like something that we don't really recognize that easily. But 4 times 14, that's shouldn't be that hard. That's 56. Okay, in decimal, that's 56. So we're adding decimal 56 to the ESI address, and decimal 56 is hex 338. So if I add 3 to E, this is going to be a 1. I think it's going to be a 1, 1 E right there. Let's see if I'm right. So let's go to, well, we're looking at primes. So the address of this is 116. Its last 3 digits are 116. So this one's going to be 4 higher than that, which is going to be 11A, because A is 10 in hex. And then 4 higher than that is 14, which is E, so 11E. Actually, I did it right in my head. I'm a little proud of myself there. All right, so the address of this last number is 11E, and that's exactly what we get when we add 4 times 14 to this address in register ESI right here. So it's going to do this calculation. So this is all going to be done in one step. It's going to calculate the address, grab the contents of that location in memory. It's going to grab this 47 and copy it into register EAX. So when we do the step over, we should see a 47 go into EAX. So boom. And sure enough, we have a 2F. So what is 2F? Well, that's 2 times 16 plus 15. So 2 times 16 is 32 plus 15 is 47. So yes, that's a hexadecimal 47. It's all good. We change it to a decimal view. We see, surely enough, there's a 47 there. And if we really want to see what it looks like in binary, we can do that too. That's what's really in there, is this binary number, right? Everything, all this stuff that we convert to characters and decimals and ASCII, it's all really binary. You should always kind of keep that in the back of your mind. It's all really binary. Okay, so there we go. We got the 2F in there. So now we are ready to move what is in EAX out to the 4 bytes starting at that address. So that's calculated the same way. And that should take us to elsewhere. Now EBX is just 0 and EDX is currently 80491188, right? You can double check. EDI is 80491188. 80491188, that's the address of these bytes here. I'm going to change this to a bytes view for the moment, and hexadecimal. And now we are going to copy what is in EAX to the first 4 bytes of this row here, of this first row here. So let's watch that happen. Step over, and boom, there it happened. So now we have 2F000000. Wait a second, that 2F is first. Why is it first? Because little endian. So when we take a number, a hexadecimal number, or a binary number, 4-byte number, 4-byte word here from registers, when they get out to memory, the order gets reversed this way. Now, I haven't really talked about why little endian is what it is. There isn't really a particularly good reason why. It's more of a why not. It basically means that the higher addresses represent the bigger bytes of multi-byte numbers. And depending on how you decide to list the contents of memory, then maybe you would think of that as being in the correct order, not the reverse order, okay? It just kind of, so just think about it as historically, this is the way it was done, but somewhere along the lines, we think of the addressing in terms of increasing order. So, you know, left to right here is the way we're displaying these addresses because that's in order of increasing addresses, right? That's just how it is. I mean, physically inside the computer, it really doesn't matter which way you choose to go. You just kind of have to pick one. So that's just the way they're designed. That's the way the addressing is done. So we're just kind of stuck with a lot of computer architectures use little endian. And we're just kind of stuck with that in terms of the way we happen to visualize the memory versus visualizing the actual numbers stored in the registers. So there is no compelling rhyme or reason why little endian has to exist. It just kind of does. But at any rate, I keep harping on it because it's the sort of thing that, you know, if you hear it enough, you're just going to remember. Deal with it enough, you're just going to remember. So here we moved this register value out to memory, and the little endian conversion happened, reversing the order of the bytes there. So now we're ready to go. We're going to decrease EBX, or we're going to increase EBX and decrease ECX. Let's do a couple steps there so we see ECX and EBX change. ECX is now D, and EBX is now 1. Now, hex D, that's a 13. So now when this address gets calculated, it should be looking at the next one down. So it should be looking at this 43 here. And when the destination address is calculated, it should be looking at the next 4 bytes on the first row, as we're displaying them here. Of course, we have to do this comparison to decide if we want to jump back, and actually, we don't need this. But I put it in anyway, just kind of for completeness and just as an example of a comparison instruction. So we're comparing ECX to 0, and then we're going to jump if greater than or equal to back to the beginning of the loop and move the next word or the next double word. But now seems like a good time to say why we actually don't need this. We don't need it because as soon as you decrement ECX and it goes below 0, it's going to set the same flags that compare is going to look at. So the decrement is just subtracting 1 from ECX. If ECX is 0, you subtract 1, it rolls over. If we're looking at it as a signed number, it rolls over to all 1s. Okay, the bits in that register become all 1s. So the first bit, so the fact that the first bit changed to a 1 sets the sign flag in E flag. So if we look at the definition of these flags here, we should find that the sign flag was set. Oh, of course it's not set yet because we're not below 0. I was like looking at it and I was like, wait a second, I told you something wrong because the sign flag's not set. But we're not at 0 yet, okay? So it's still positive, so no sign flag set. The other thing that will happen is the carry flag may or may not be set by an operation. And it's actually deciding whether the previous comparison or the previous subtraction resulted in something less than 0 or resulted in a less than situation. You actually have to look at both the sign flag and the carry flag. And currently those are both set to 0. They're equal, which tells us that the comparison, that the subtraction did not go from a positive to a negative. And here, when we do this comparison, they'll still stay zeros. So again, remember our flags. The flags we're looking at, if we come over here, we want to look at the 5th bit from the right and the 1st bit. Okay, 5th and 1st. So let's do a step over, and that comparison is essentially not less than, so the greater than or equal to is going to be true, and we're going to jump back, and then we're going to step through again. And again, and again, and again, and so forth. And we should be seeing, if we look at elsewhere, we should be seeing it fill in. So we see the 2F there, the 2B there. Now let's go ahead and change these to 4-byte words. Incidentally, remember when I said that words mean different things in different places? Or the word means different numbers of bytes to different people in different times and places. So in our assembly language, a word is 2 bytes and a double word is 4 bytes. But here in the K debugger, 2 bytes is a half word and 4 bytes is a word. So that's not confusing, is it? You just have to remember. Maybe it's just better to say 4 bytes, 2 bytes, that sort of thing. Or to just always say the size of your word when you're talking about words. 2-byte word, 4-byte word, 8-byte word, 1-byte word, that sort of thing. So right now we want to look at 4-byte words, and let's go ahead and look at them as decimal numbers. So there we go. We have the 47, 43, 41, 37 in there. And if we keep stepping over, we see them filling in as the ECX counts up, or ECX counts down, and EBX counts up to index the location of source and destination so that these end up reversing. So again, remember they were in forward order over here. So 2, 3, 5, 7, etc. up to 47. And in the destination, they are going down, 47, 43, and so forth. And we're just filling those in. So we keep it going around until it's done. 11, 7, 5, 3, and the last prime is 2. Actually, the first prime is 2. We decrement ECX. Now notice that the sign flag is 1 and the carry flag is 0. They're not equal. And we step again. Oh, Oh. Wait a second. ECX just flipped. Notice, let's take a look here. ECX rolled over. Then we did a comparison of ECX to 0. So remember that all ones, if we interpret it as a signed number, all ones is interpreted as negative. Now it is up to us to make that interpretation. Okay? But you know what? I think I may have lied to you about not actually needing the comparison. I'm going to have to... We might have to just take this out and see if it still works. If I looked at what happened with the flags here, it wasn't what I was expecting on the decrement command. Maybe the decrement does not set the flags that I expect it to. But at any rate, let's keep going forward. This way we know works. When in doubt, use the compare instruction so you know you get the flags set the way you want them to. I guess that's the lesson there. I was thinking that we would get away with not needing that, but I saw a flag change here that I wasn't expecting to change. So let's go ahead and see that this should now take that result, which we're basically saying this is less than 0 if we interpret this as a negative number. Okay, so what happened was it did a subtraction, and as I've told you, the CPU doesn't really know if it's subtracting a signed or it doesn't know if it's subtracting signed or unsigned integers. Okay, it doesn't care because the exact same thing happens either way. It's up to the software and what jump commands you use and how those things look at the flags that decides whether or not we consider this all F's here as a 2's complement -1. So for our purposes, that's exactly how this is going to interpret that. We can basically treat it as having gone negative, so it's now, we took a 0, subtracted 1 from it there, it's a negative number, so when we compare to 0, it is less than, so it is not greater than or equal to, so we will not make this jump. So we step, and then we are on to the last 3 instructions of the program, where it's just setting up a nice clean exit using the system call to sysexit. So we might as well just click run and let it run itself out. So this program does not produce any output, does not take any input, it just does everything in memory, but it serves as a pretty nice example of the ways in which you can use indirect addressing, indirect operands to address memory and to work with arrays, to step through the items in an array and so forth. And you always have to make sure that when you have arrays of things that are more than 1 byte, you have to remember what size you're working with. Most commonly we'll be working with either bytes or 4-byte words. Maybe we'll do something with 2-byte integers at some point, but generally speaking, we're either going to work with characters or words. We're not going to get into anything more complicated than that. Maybe we'll look at things that kind of operate as the way, if you remember structures from C programming, we might end up looking at something like that somewhere along the line. But that's going to be quite a ways off, if we look at it at all. So that wraps up what I want to talk about. I'm actually going to have to double check what I said here. I didn't test this before I wrote this comment in that we don't actually need this comparison, because now I think we do. I'm going to have to double check that, and in the next video I'll explain yes or no whether I was right about that, because what I just saw happen in the flags there makes me think that I goofed. and had it wrong what I could do with that decrement. But I will say is that in general, these jump instructions, jump greater than or equal to, and so forth, all they are actually doing is looking at flags, and regular arithmetic operations do set flags. So if you know what effect an arithmetic operation will have on a flag, then you can use these jump commands even if you didn't use a comparison immediately before it, as long as you figure out the right jump command for what you want to have happen. So that's the main underlying point. The fact that I probably, judging from what I saw in the flag register, I'm probably a little bit wrong about, a lot wrong. There's either right or wrong. I think I'm probably wrong about not needing this compare operation to make this work, so we can't actually leave it out and have it work. But I will double check on that. For now, I need to wrap this video up, and so that's it for video number 3, week 5 of assembly language.